I think in a lot of climate conversations, often the place people start, because they think about cars, and it is a big part of the problem. There's obviously a lot more to that. But you guys have very different takes on how to sort of solve for this problem and make a cleaner transportation system. Tony, maybe we start with you and talk a little bit about modern hydrogen.
Sure. Hi, everybody. So very quickly, we're a relatively young energy company in this energy space. We are 8 years old, and we produce clean hydrogen at the points of use actually through decarbonizing natural gas. So we turn natural gas into clean hydrogen without any CO2 emissions, and also by taking captured solid carbon, we actually sell that to make roads for the asphalt market. And so on transportation, so first of all, our company is, in some sense, application agnostic to hydrogen. We're in charge of making sure the hydrogen is produced in a clean fashion and is available for cheap economic costs on sites where you want it. So of course, one application is building hydrogen refueling stations. But generally speaking, really, some of our customers are utilities, are placing our boxes, all sort of places, industrial decarbonization and so forth. I actually would be I put a huge asterisk on hydrogen for transportation. I think for many applications in transportation, hydrogen doesn't make any sense whatsoever. I don't know what Toyota is doing with the Mirai, but I think for light vehicles, electric cars are clearly the way to go. Transportation is too large. You're not getting a one-size-fits-all solution. I think when you look at things like energy density, then you get to some transition point. If you have to go very far and you have to carry very large loads, at some point you don't have enough energy density in a battery and you need to go to something else, and that's why hydrogen becomes interesting. So all our conversations on hydrogen is not for light vehicle refueling stations. They're all about long-haul trucking along the highway or municipal bus fleets and so forth.
Yeah, great point. And that's a great point. And Josh, you also, you're in the transportation industry, but you're not putting cars on roads. You're trying to solve the problem of what happens to these batteries after they come off the road.
Yeah, absolutely. It's almost the opposite, right?
Yeah.
So yeah, I work at Reliant Energy. We are an energy storage systems provider. What we do is we take second life batteries, so batteries previously used in electric vehicles, typically leased vehicles. When the batteries come out of the vehicle, often they'll have a lot of energy left in them and a lot of life left in them. So we repurpose them for stationary energy storage for commercial and industrial users as well as utilities, and we deploy those on the power grid.
So you're basically building power walls, but not Tesla-based. Not new batteries, old batteries.
Yeah, large versions of that. So yeah, a typical system for us is the equivalent of about 50 or so Tesla Powerwalls. And then it goes up to that big utility scale power plant.
Does there come a point where, how do you recondition the battery? You recondition the batteries? Is there a point where they're just dead and they're completely useless?
Yeah, so what we come across, so I guess to provide a little more context on our company, so the special sauce that Reliant has developed over time is our battery management system, which extends the lifetime of batteries. So it can apply to new batteries, it can apply to old batteries, it can apply to batteries that have 80% of their starting capacity or 20% of their starting capacity. What we run up against is batteries that are really low in terms of how much capacity they have left, is that it starts to not become cost effective to repurpose them. It's not worth the time to recertify, test them, and then put them in a container with a bunch of other batteries, because that space in the container could be used by a battery with more energy left. So typically we tend to focus on batteries that have more than half of their starting energy capacity. And the process for them, there's a lot of screening we have to do up front to make sure the battery is healthy, that it doesn't have any physical defects, that it's going to be safe to continue the life of that battery. Once we do that, we go through the process of designing a system that will be able to utilize that. Our software and controls are really plug and play, so they can work with any kind of battery. But we still have to do the electrical design based on the voltage of the battery and other physical characteristics, thermal requirements of the battery, et cetera. And then once we've designed the system, we need to go out and certify that to UL standards for safety purposes, and then we can go and deploy that. So multi-step process, skipping over a couple steps there, but yeah, that's the high level of it.
So what happens, and I don't know the answer to this question, I should, like a lawyer, before I ask it, but what happens, you're reclaiming electric car batteries, what happens to electric car batteries that are not reclaimed in this way? Where do they go?
Yeah, so the lithium-ion battery recycling market in the U.S. has really taken off, and the Department of Energy Loan Programs Office has been a huge supporter of like Redwood Materials, American Battery Company, Li-Cycle, Servo Solutions. There's a bunch of these providers that are building. Typically, they build recycling plants next to where new battery production is being built. There's two reasons for that. One, their customer is right there, so they can take the raw material from recycled batteries. And I should have said, what they do is they mechanically break the batteries down and salvage, copper, nickel, sometimes cobalt, and lithium, and sell that to people manufacturing batteries. So they'll sell it back to the people producing it. The second reason they put themselves next to new battery production is when you start a new battery facility, lithium-ion batteries are extremely, extremely sensitive to defects. So in the first year of operation of a new battery plant, about the scrap percentage is over 50%. Nope. So over half the batteries actually go back to recyclers. So the recyclers today are really, most of their business is manufacturing scrap, and that's slowly changing over time to be more EV batteries. And we are basically a step in between the first life of the battery and the scrap or recycler is the second life application.
Very cool.
Yeah.
So Tony, when you talk about, I think I take your point about transportation and hydrogen and how that's how people usually begin to think about it. But what are some of the other applications you think that you could move into?
So firstly, even in transportation, we've been talking about cars and trucks, but transportation is everything also from rail, ships, and planes. And there's definitely many efforts to work on hydrogen for planes and shipping, all of which is hard, but there's really no good solution. Like if you do the calculation of trying to fly intercontinental with a Boeing 747 powered by electric batteries, like you'll never be able to do it. It's like it violates like chemistry and physics. So that's why there's these interesting applications for hydrogen or hydrogen-derived fuels. So you can make clean hydrogen and then use it to make what people call like e-fuels, sustainable aviation fuels. That could be a solution for these systems where you just need the 50 times larger energy density of a fuel instead of an electrochemical battery. But in addition, actually, my favorite example of hydrogen is actually making stuff. So we feed the planet with fertilizer. Fertilizer, key ingredient in is ammonia, NH3. That hydrogen is itself today made from natural gas, a fossil fuel, with an extremely polluting process, emits a bunch of CO2 into the atmosphere. But this hydrogen is used to literally make foods. Like you and I cannot swallow a clean electron from solar. If we stopped making that clean hydrogen in our car, if we stop making that hydrogen, it's not clean today, but if we stop making that hydrogen in our economy today, given that half the nitrogen in your body right now is derived from that synthetic fertilizer, if we stop doing that, half of us will have to die. So that gives you an example of like the need for these other solutions, including hydrogen, to decarbonize other parts of the economy, because transportation's like a bit more than a quarter, right? But manufacturing's a lot. Making materials is a lot, powering industrial processes. The other thing that you see is half of final energy demand is heat. And about half of that is industrial heat, which is very high temperature. I won't get into the physics, but for low temperature heating, like if you're heating your house, there's something magical called the electric heat pump that can use renewable electricity. You have a leverage effect, and you can produce like low-grade heat that's perfect for heating a house. Great solution. It is physically impossible, violates laws of the universe, to try to create high-temperature heat with an electric heat pump. Like it's something called Carnot efficiency. It just won't work. Right, making concrete has a step that involves like 1500 Celsius. You've probably seen pictures of metal and steel factories, molten vats of metals. These are over 1,000 Celsius. How do you decarbonize that? Electrification probably is going to really struggle there, and so people are exploring things, including burning like biofuels, but hydrogen is another one of those solutions.
So what I've always heard about hydrogen is that it's a fantastic fuel, but it winds up costing more to create, and before you wind up using more energy to create it than you can get out of it eventually. What is it about your approach that bypasses that?
Yeah, so our approach is an economic approach and not actually a thermodynamically efficient approach. Because again, I'm a physicist by background if you haven't figured that out yet.
I think they're getting the idea.
There's no free lunch, right? So our trick is, so natural gas is the cheapest fuel source in the United States and many countries. We use so much of it, so I'll give you a sense, right? We use as much natural gas as coal, plus nuclear, plus wind, plus solar, plus hydroelectricity. All that combined, same size of natural gas. So it's abundant, it's cheap, and when we burn it, it emits a ton of CO2. And there are 2 panels that go, like even getting natural gas, there's a lot of upstream emissions. So we do need to clean it up. But the trick is, natural gas is chemically CH4. So it's like 80% hydrogen atoms already. What you really don't like is the carbon atom. When you burn that creates CO2. So we have developed a technology to crack the molecule. And the key thing is when you do that, that's not free. You take some energy to do that, but more importantly, we don't burn the carbon. And that's actually the major energy loss in this process. So we are less efficient than just burning the fuel. So that's bad, right? The trick economically is we sell that carbon as a useful material for 10 times the value than what it would have been worth just burning it into high value materials. For us, that is like making roads, like making asphalt. So really, yeah, thermodynamically, you can't win. But you have to find some useful things to do with the byproducts and process to make this actually economic benefit so that you don't have to rely on government subsidies to make this work.
Yeah, and you can hear that theme has come up a couple of times today in terms of harnessing the waste stream. Yeah. But to end on policies, we just passed the IRA. We were here a year ago. Everybody was very excited about all the money that was going to be flowing through. As I was programming this conference, a little less enthusiasm today. It seems like the money may not be going to all the right places, particularly maybe not going to startups, which I think something we'll be talking about in the next session. But how do you see the policy framework today, and how have each of your companies benefited or not benefited by the current policy infrastructure?
Sure. So the IRA has been a very interesting one for us. There's also state policies, which are very interesting. What we come across with the IRA, first of all, IRA has been huge for energy storage in general. The IRA took the 30% investment tax credit, which was available for solar projects, and in many cases hybrid solar plus storage projects, and made it so you can apply it to standalone energy storage. What's complicated for us is we're taking batteries that have been used in an electric vehicle, which hypothetically someone else has already taken a tax credit on. So the IRS is trying to figure out how exactly they treat our systems because they don't want people to double dip. So we're part of an industry group trying to figure that out. But part of being a startup is you're in new territory and you're going through use cases that policymakers haven't really thought about before. And there's a lot of senators and Congress people who come from districts where they're building new battery plants, and they would rather batteries go to the recyclers and get remanufactured as opposed to being used in a second life, right? Because it improves employment in their district. So it's a politically, I don't know, lack of a better word, tedious kind of process for us as far as the IRA goes. There's also state level programs. So in California, a lot of batteries at the commercial industrial level get deployed through the Self-Generation Incentive Program, or SGIP. SGIP specifically prohibits second life batteries currently. I talked to the program.
Why would that be?
So the assumption was that you couldn't get enough lifetime out of second life batteries because SGIP wants to deploy systems that can support the power grid for 10 years. So again, because we focus on extending the lifetime of battery, our standard warranty is 10 years. We've done 15 or 20-year warranties with second life batteries. So I've gone to them and say, hey, why didn't you make the requirement 10 years of warranty? Because there's first life battery providers who only provide 5 or 7-year warranty, which is worse terms than what we do. And they said, oh, that's a good point. You should file a regulatory proceeding, and then we'll get to it. I'm like, SGIP's going to run out of funding in 18 months, and I've seen, so anyway, it's not worth it. So there's nuances and things like that you have to come across that you have to deal with. Obviously, a big part of educating regulators is that hopefully you turn the tides and they start seeing the benefits of the new technology and things they just hadn't foreseen.
IRA. So I actually want to give some credit to Congress, at least in our sector in hydrogen. The initial law in the IRA, and credit to Joe Manchin, for startups, for us, made a lot of sense. They decided, okay, government, we're actually not very good at picking winners and losers, but what we care is the cleanliness of the hydrogen production. So the credits was a nonlinear subsidy towards how clean your hydrogen was. Basically said, okay, let's just literally, you have to follow a Department of Energy formula, calculate how much CO2 emissions like literally how many kilograms of CO2 is emitted per kilogram of clean hydrogen that you produce. And the cleaner you are, the more subsidy we'll give you. We are not going to pick any specific technologies, but everybody go through a fair measurement process, and we're just going to reward disproportionately the cleanest ones. At least that to engineering technology firm, clear goal, aligned with what we want to do, decarbonization, everybody work towards it. Now, what's really happened is ever since the IRA passed 18 months, then the detailed implementation of the rules became this crazy lobbying special interest, sausage-making fights until this day. The final rules are still not determined 18 months later, and that's why some of this money is not flowing. And that's actually cooled down some of the investment into the hydrogen space. That being said, like, fortunately, the IRA is not the only game in town. So my company, our biggest supporters, investors, and customers tend to be utilities. So to give you a sense, right, NextEra, the largest utility in the country, actually the biggest renewable energy developer in the world, is both a customer and investor of ours. Also National Grid, one of the few multinational utilities in the world, et cetera. And so when you're a utility and you are under pressure to decarbonize, a lot of that's actually coming from the states level. And so actually, for us, like we already start getting traction for our solution to help the utilities decarbonize their hydrogen even before the IRA. And I think we'll see what happens with the IRA and what happens with the election. But generally, I think we are doing business planning where we treat the IRA as a cherry on top, but that's not the main thing we rely on.
Excellent. I think we've got time for a question if there's a quick one.
Hi, my name is Mrinalini. My question is towards Josh. Actually, when we talk about second life of a product, we always have to justify it with the help of like a techno-economic analysis. What was one of your main challenging factors in proving, I would say, cost-benefit impact of what your company is doing, and how did you guys overcome it?
It's a great question, and it's an ongoing one. Or the answer is one that is going to evolve, and if you ask me a year from now, I will probably have a slightly different answer. But for what we're doing, our final product is a fully packaged energy storage system. So it's basically imagine a shipping container chock full of batteries with an inverter, fire systems, heating, cooling, and some other electrical components. So you drop it in place, and it's ready to go with the power grid. The reason I bring that up is that in the context of your question, the batteries are reused, all the other components are new, which, to go back to the IRA question, actually helps us in qualifying for domestic content, and there's some interesting nuance there. But what we need to figure out is, okay, if our cost advantage comes from having lower cost battery modules, how does that compare to first life battery modules, which in itself is a moving target. I was talking with some folks over lunch. Raw lithium prices at the beginning of 2023 were about $75,000 a ton. Right now they're about $15,000 a ton. So the cost of batteries, first life batteries, has gone down a lot in that reference point.
Why is that?
A few reasons. Mostly, I think the short version is that lithium production caught up to demand. There's a lot of headlines, obviously, about EV demand growth not being as strong as it was. There's also been some large battery energy storage, grid energy storage projects that have kind of slipped out in their deployment schedule. So lithium production that came up, that has been in the process of coming online, has finally come online, and the commodity market has kind of adjusted. For reference, 15,000 is about where lithium was 3 years ago. Okay. So there was this bubble while lithium production hadn't caught up to demand, and now it's kind of caught back up. But bring it up to say that's a moving target, and it's an analysis we have to keep doing. We're actually, because our core technology is around extending the lifetime of batteries, there are applications of what we do for first life batteries. We still believe the circular economy narrative is important. We think there's benefits to it, and we still plan to do that. But it's something we have to continuously benchmark, and I've got probably more Excel models than I need to have, basically backtracking the numbers of publicly traded energy storage companies and what their margins are to figure out their costs and how the module costs factor into that and compare it to our module costs. So it's a very dynamic market, and the way we look at it, we really look at the module cost comparison and making sure that we're able to stay ahead given the lower cost modules we get versus the typical first life battery.
Very cool. Well, guys, thanks so much for sharing your knowledge with us. I hope everybody took notes because I wish I could take more while I was on stage with you. But I learned a lot. Thank you so much for the
Great,
time.
Dan. Thanks.
Thanks a lot.
Thank you.